Hello and welcome to this C105 video. So today we are going to talk about the hardness of glasses. So in the previous chapter we started to talk about the stiffness of glasses, which characterizes the glass resistance to reversible deformation. So you apply a load, you see how much the glass is deformed, and then when you remove the load, this deformation is reversible, which means that the glass recovers its initial shape. Here we are going to talk about the hardness of glasses, which characterize the resistance of glasses to irreversible deformation. That is to say, when you apply a load and that the glass doesn't recover its initial shape, that you have a permanent indent or permanent scratch at the surface of the glass. So this is probably a property that is even more important than the stiffness of glasses. Stiffness of glasses is pretty important, but for example, smartphone screens, what's more important is not how glass deforms elastically, because elastic deformation are reversible, so they are not going to damage the glass surface. But what's more important is the hardness, because if you, for example, have your keys and you try to scratch the screen of your smartphone, you don't care about the instantaneous reversible deformation. What you care is how the shape of the glass will be modified after you have applied the load with your keys. What you care is potentially the presence of a permanent indent or a permanent scratch at the surface of your screen. So that's why optimizing the hardness of glasses is very important, especially for cover screens that are used for protection on a smartphone screen. So in this chapter, what we are going to see is first, what's the definition of hardness? How do you define it? How do you measure it in practice? And then we are going to see how hardness depends on the structure of the glass and how you can use some information about the structure of the glass to predict its hardness and to find optimal composition that meets the level of hardness that you want for a specific application. So let's first focus on what's the definition of hardness and how hardness can be measured in practice. So the definition of hardness is that, the general definition is that hardness characterizes the resistance of a material to be permanently deformed by another one. So the idea is that if you take two materials, one that is hard and one that is less hard, and you try to scratch one on each other, the idea being that the harder material, the one that has the higher hardness, is going to scratch the material that is less hard, and not the opposite. A material that is less hard will not scratch a material that is harder. So for example, if you take a knife and try to scratch a piece of glass, then the knife is going to scratch the glass, but the glass is not going to scratch the knife. So the idea in that case is that the metal that the knife is made of is harder than the glass. And that's a general definition, that harder material, the material that have a higher hardness, will always scratch the one that have a lower hardness. So a first possible definition for hardness is that you can define a scale, and every time you have a new material, you can try to scratch it with all the other material, and you check which one is scratching the other, and that way you can make a ranking of materials based on which one is scratching the other, and based on that you can define a relative hardness of material. So this idea of a relative scale of hardness for material is actually the base of the Mohs hardness scale. So what we will see in the following is that there is not a single way to define hardness. Hardness is not really a material property. For example, Young's modulus is a material property. For each material, you have a given Young modulus. It's because the Young modulus has a clear definition. This is the stress that this is the proportionality constant between the stress and the strain. So if you take a material, you apply a given stress, you can measure the strain, or you apply a given deformation and you can measure the corresponding stress. This gives you the Young's modulus. For hardness, there is different way to measure hardness, and each way of measuring hardness will give you a different value. So usually we can always define what is the material that is harder than the other, but when it comes to the specific value, then it depends on the method that you are using. So the first way of characterizing the hardness of material is this Mohs scale of hardness. And the idea is to take a selection of 10 material going from diamond, quartz, calcite, etc., and to scratch each other on top of each other. So the idea, for example, is that you take diamond, you take quartz, you make them go in contact with each other, and you check which one is scratching the other one, which one is permanently deforming the other one. What you would observe is that diamond, which is the hardest material, is deforming quartz, diamond is scratching quartz, but quartz is not deforming diamond. Quartz is not scratching diamond. Why? Because diamond is harder than quartz. So the idea is that in this scale, based on this selection of 10 materials, you try to scratch them on each other. In each case, you check which one is scratching the other one and which one is not scratching the other one. And based on that, you make a ranking from the harder to the less hard material. What you find is that diamond in that case would be the hardest. In that case, you assign a hardness value of 10. In that case, the hardness doesn't have any units, it's just a value of 10. Then, for example, you take corundum. Corundum is not scratching diamond, but corundum will scratch all the other 8 materials. So in that case, you assign the value of 9 to corundum, etc. You find that quartz will not scratch diamond, will not scratch corundum, will not scratch topaz, but will scratch all the other one. In that case, you assign the value of 7 to quartz, etc. Talc being, in that case, the material that has the lowest hardness, which means that all the other 9 material are actually deforming talc. Talc is a material that is not very hard. And then, based on this reference, what you can do is every time you have a new material that is not in this scale, for example, you take a steel nail or a knife or etc., or a piece of glass, and then you try to scratch it with your reference material. For example, you take diamond, you try to scratch glass with diamond, you will find that diamond is going to scratch your glass, which means that glass has a hardness that is lower than 10. Then you can take quartz and you try to scratch the piece of glass with quartz. Again, you find that quartz is scratching the glass, but glass is not scratching the quartz. That means that the glass has a hardness that is lower than quartz, etc. And for example, you would find that apatite here, in that case, would not scratch a piece of glass, a given piece of glass. In that case, it means that the piece of glass has a hardness that is higher than that of apatite. In that case, if you continue like this and if you try all the reference material, if you find that autoclase is scratching glass but apatite is not, that if glass is actually scratching apatite, then it means that the hardness of glass is in between 6 and 5. So for example, 5.5. And what you can do for this is, for all the given material, you try to scratch them with your reference of 10 materials. And based on that, you can define the hardness of all materials based on which one is going to scratch and which one is not going to scratch, which one is going to be scratched by the material. For example, you take the fingernail. A fingernail is going to be scratched by calcite, but is going to scratch gypsum. In that case, it means that the fingernails, the hardness of fingernail is going to be between 2 and 3. Although the Mohs scales provide a pretty intuitive definition for hardness, it's not very convenient to use the Mohs scale for glasses. The reason is that most glasses are pretty much in between apatite and quartz, which means that the hardness will always be between 5 and 7, which is not very good to really closely distinguish different glasses with different hardness. So this scale is not so appropriate for oxide glasses. The other reason that this scale is not so appropriate is that it's mostly qualitative, like it's arbitrary. It depends on the choice of the 10 material that you choose to define what has a hardness of 10, what has a hardness of 9, what has a hardness of 8. This choice is arbitrary. It doesn't mean that diamond has a hardness that is 10 times larger than the hardness of talc, for example. So this just depends on the material that you choose as a starting point to define your scale. So overall, this Mohs scale, although it is useful and although it's pretty intuitive because it's based on the idea of which material is going to scratch the other one, it's not very much used in practice because it doesn't provide a very quantitative value of what hardness of a given material is. A more appropriate way to define hardness and to measure hardness is to use indentation tests. So the idea is that you take a glass surface and you approach an indenter and you apply a load. So this would be, in this case, the indenter. This is here the glass surface. What you are doing is that you are applying a load P with the indenter, and then you are removing this load, and that way it provides a way to measure both the elasticity of the material, so how much it deforms in a reversible way, and also how much it deforms in an unreversible way. So it provides a way to measure the hardness of the material. So there is not a unique definition of hardness even measured by indentation, because first there are different types of indentation depending on the size of the indenter and depending on the kind of load that you apply. You can have nano indentation if you have very small indenter and very small load. Or you can have micro indentation or macro indentation depending on the size of the indenter and the type of load that you will apply. So different types of indentation will give you different hardness, and you can also have different geometry for the indenter. You have some indenter that are more spherical, some indenter that are more like a pyramid, some different shape. So again, different shape will give you different values of hardness. That being said, the definition of hardness more or less always rely on the same idea, that you start with an undeformed glass surface and you approach an indenter. So again, the indenter can have different geometry, but it's always some kind of pointy or a spherical shape like this. And you start to apply a load. So as you apply the load, the indenter will start to deform the glass, and the glass can deform in different ways. First, part of the glass will deform in an elastic fashion, but part of the glass will also deform in a plastic fashion. And as you remove the indenter, so this is when you apply the load P, if now you remove the indenter, some part of the glass will come back to its initial shape. So this is the elastic deformation. The elastic deformation will be recovered after you remove the indenter. But some of the deformation, the plastic deformation here, will not be recovered after you remove the indenter. So you will have here some elastic deformation, but also some plastic deformation that are not recovered after you remove the indenter. So the idea being that when you apply a load with the indenter, you always have to measure what is the area of contact between the indenter and the glass. And one way that hardness is typically defined is to say that hardness is equal to the ratio of the load that you apply. So this is the load, so this is a force, divided by the area of contact. So the area of direct contact between the indenter and the glass. So this is the area of contact. So that way you have a load which is in Newton, this is a force. You have the area of contact which is in square meter, this is a surface, an area. So that way you define a hardness which is a force per unit of surface, so it's a pressure. So the hardness will be in Newton per square meter or in Pascal, but typically, at least for glasses, for oxide glasses, the right unit of hardness is more on the order of a few gigapascal. So the idea is that this quantity defines the resistance of glasses to permanent deformation. For example, if you had a glass that would be perfectly hard, that would have an infinite hardness, that would deform only elastically and not in a plastic irreversible fashion, what would happen is that you start by your glass surface, you approach the indenter is deforming the glass, but the glass is only deformed in an elastic way. In that case, the area of contact would be zero. The contact is only limited to one single point, so the area is zero. And in that case, it means that if the area of contact is zero, then the hardness would be infinite. So in that case, this is for an infinitely hard material, the hardness would be infinite. This is for a perfectly elastic material. In that case, the hardness would be infinite. So starting from this, as soon as you have a little bit of plastic deformation, as soon as the glass actually deformed and that you have an area of contact that forms between the indenter and the glass, then the hardness will not be infinite anymore, and you will have a different value. On the other hand, a glass that would be perfectly soft, that would just fully deformed with no load being applied, then would have a hardness of zero. So you have this range, all this possible range of values between a hardness of zero for a material that would perfectly deformed with no load being applied, like for example, like a liquid would have a hardness of zero because you don't need any load to deform the liquid, and you would have a hardness of plus infinity for a perfectly elastic material that does not that doesn't deform in an irreversible fashion, that only deformed in a fully reversible fashion, which means that if you have a fully elastic material, after you remove the load, after you remove the indenter, the material goes back to its initial shape with no permanent indent, no permanent deformation, as opposed to a material that has a non-infinite hardness. Here you would have a permanent indent at the surface of the glass. So typically this formula, this equation, load divided by the area of contact, gives you the value of the hardness. And again, for oxide glasses, typically you have something that can go between 1 to 10 gigapascal. This is a typical value for the hardness of oxide glasses. Here you can see a few hardness value for a few select glasses. So overall, for silicate glasses, the hardness is typically between 5 and 7. For example, here you have a few hardness value for some alkaline earth, alkali silicate glasses, which is around 5 to 6. The value for pure silica, the hardness of pure silica is around 7. And this is the value here for soda lime glass. So this is a typical glass that is used for window glasses, hardness of around 5.5. The highest hardness in this case is achieved for oxynitride glasses, which gives you a hardness of 10, which is a pretty high value. And for example, this is the typical value for bulk metallic glasses, hardness of around 5. So now what we are going to do is to look at what are the different mechanisms when you indent a glass that can contribute to its hardness. What are the different ways that glasses can show some plastic deformation. So it's important to understand these different mechanisms to be able to understand in turn how the composition and the structure of glasses is controlling the propensity for those different mechanisms that are going to control the hardness of glasses and their propensity for non-reversible deformation. So this is what a typical indent looks like. If you take a zoom picture on what the surface of the glass looks like after you have indented it, this is what it typically looks like. So you have a hole here, which is the indent. So this is the permanent deformation that is applied on the glass after the indenter has been loaded and unloaded. But what you also see potentially is the formation of cracks at the corner of the indenter, or you can also see the formation of some pileups here. It means that when you apply the load, typically you will have some shear deformation. That is to say, you will have some material that is pushed here from the middle, from the point where the glass is indented, and is pushed towards the edges of the indent, and you have some pileups that form on the edges of the indent. It means that you have some displacement of glasses that somehow flows from the area where you have high load values towards the edges where you have a lower stress being applied. So this is pretty important because it tells you that there are two main different mechanisms that can contribute to decrease the hardness of a glass. The first thing is that if you apply a load here with your indenter, the first thing that the glass can do is to permanently densify. It means that the glass will just compactify, the atoms will come closer from each other, you will have some internal porosity within the network that will be lost, and the glass will just be compressed, permanently compressed, will just occupy a lower volume. So the same number of atoms will come and form a denser network that occupy a lower volume. This is the first thing that can happen in a glass. This is the first way you can create an indent. When you create an indent, you are reducing the volume of the glass, and one way to reduce the volume of the glass is just to for the atoms to come closer from each other. That is to say, to have a glass that shows a permanent densification. So permanent densification is the first thing that can contribute to the hardness of a glass. The second thing is to have a displacement of matter. Instead of having a permanent deformation here under the indenter tip, another thing that can happen is that the indenter will permanently displace the glass from the region where the indenter is coming in contact to the glass towards the edges, and in that case you have some pileup forming. In that case, this is not a deformation because this is not a densification because the volume is conserved. It's just a displacement of matter. So in that case, whenever you have a densification, so with this we will call it a permanent densification. The permanent densification is whenever the glass shows a compaction, a permanent compaction that is not recovered after you remove the indenter. But the other mechanism that can happen is a displacement from the region where the indenter is applied to the edges. In that case, you have the formation of some pileups, and in that case, we will call it a shear flow. Shear flow is when you have a displacement of matter from the region where you have the load being applied. This is where the load is applied to the edges where there is no load applied. In that case, the shear flow is not changing the volume, it's just a displacement. The material, the glass, is being displaced from one region to another, but the volume is remaining the same. In that case, you can call this isochoric. Isochoric means that the volume is conserved. So in that case, volume is constant. The shear flow is just a deformation at constant volume where you have a displacement of glasses, as opposed to the permanent densification where in this case the volume is changing. You have a densification, a compaction of the glass under the load. And those two things, both shear flow and permanent deformation, can contribute to increase the area of contact between the glass and the indenter. So both of those things are going to control the hardness. The hardness is the load divided by the area of contact. So there are two ways you can increase the area of contact: by increasing the level of permanent densification or by having more shear flow. So those two different mechanisms, the more shear flow you have, the more permanent densification you have, the lower the hardness of the glass will be. So this is what the glass surface looks like during the indentation. So when the indenter is coming and is indenting the glass will have two behavior. First, you will have an elastic deformation. You apply a load, so the glass will elastically deform, will elastically compress, and you will also have some plastic deformation. So this curve here is the surface of the glass during the indentation, so during when the indenter is in contact with the glass. So you have two things. You have first the overall elastic deformation of the glass. This one is the elastic deformation that will be reversible after you remove the indenter. You have the plastic deformation. You have some shear flow, so some glass that is flowing towards the edges where no load is applied, and you will have under the indenter some area where you have some permanent densification. You will have a portion of the glass that is permanently densified that will not recover its initial volume after the indenter is removed. When you remove the indenter, after the indenter is removed, then the glass change its shape again. Why? Because this time you have the elastic deformation that is recovered. So all the portion of the glass that was elastically deformed will now recover its initial shape. So altogether, after the indenter is removed, this is what the surface of the glass will look like. You will still have some shear flow because this shear flow is irreversible. It's an irreversible deformation. It doesn't go back to its initial shape. You will still have some area of the glass that is permanently densified with a lower volume. This again is an irreversible deformation, so it's not recovered. So altogether you will be missing here some volume that used to be here but that is not here anymore. This is the volume that is permanently lost due to the irreversible plastic deformation. But the elastic deformation will be recovered. So you would go from the red curve to the black curve. You have some of the elastic deformation that is recovered, that is reversible, so that comes back to its initial shape after you remove the indenter. So altogether, those two phenomena, the shear flow and the permanent densification, will be the two phenomena that are responsible to determining what the hardness of the glass will be. So one way to distinguish the contribution from the permanent densification and from the shear flow to the hardness is to use annealing. So how does it work? So those two figures here, those two schematics shows you what the surface of the glass looks like after the indentation, before annealing and after annealing. So what is annealing? Annealing is that you take the glass after it has been indented, so after it has been deformed, and you heat it, and typically you would hit it at a temperature that is around 90% of the glass transition temperature, so 0.9 times Tg. So why do you do that? Because when you heat it, when you put it close to the glass transition temperature, the glass is going to be able to partially relax, which means that whenever you have a permanent densification, so here in this area you will have some permanent densification, this permanent densification will be released. Why? Because you have the glass that was permanently densified. When you densify the glass, you accumulate some stress within the structure. Why? Because you force the atoms to come closer from each other than what they would like to be. So when you heat the glass at a high temperature, you heat it at a temperature that is slightly lower than the glass transition temperature. So the glass is not starting to flow and to turn like a liquid, but the temperature will be high enough so that the glass can start to reorganize to recover its initial shape by releasing the internal stress that was accumulated when the glass showed some permanent densification. So altogether, when you anneal the glass at a temperature that is high enough but not too high, two things will happen. First, the shear flow is just a permanent displacement of the glass, but with no change of volume, no internal stress. So the shear flow will not change from before to after annealing because there is no stress. The shear flow is just a displacement of the glass, which is isochoric, which is with the same constant volume. So this is not going to change. The shear flow, the pileups that are formed at the edges of the glass, this is not going to change before and after annealing. what is going to change is that all the portion of the glass that was permanently densified will recover its initial volume, so that everything, all the region that were experiencing some internal stress because of the fact that they were subjected to a permanent densification, will now, the stress will now be released, and the volume of the glass will recover its initial value. So this is a way to distinguish the permanent densification. The permanent densification are the ones that are released upon annealing. So this part is going to be released upon annealing. Before annealing and after annealing, the permanent densification will have disappeared. But the shear flow is not going to change. It's not affected by annealing. The shear flow is a displacement of the glass. Annealing is not going to redisplace the glass. The only thing that annealing is doing is to releasing the internal stress due to the permanent densification. So by looking at the surface of the glass before annealing and after annealing, you can determine what is the fraction of the volume that was densified and the fraction of the volume that was displaced through shear flow deformation. So the way to characterize the contribution of the permanent densification and of the shear flow is to look at the topography of the glass. That is to say, the shape, the height of the surface before and after annealing. So you start by the indentation. So you perform the indentation, then you remove the indenter, and you have the surface of the glass after indentation. So this is the first thing that you have to start from. Here at this point, you can use, for example, AFM, which is a technique that can be used to look at the height of the surface according to its position. Based on that, you can calculate two things. First, what is the volume here of the pileups? So this, we call it VI plus. All the I subscript means the initial volume. Plus means the pileup. And you have also the volume that is missing here. You can calculate the volume of the hole that was left by the indentation. So this is the VI minus, the initial volume of the hole that is the permanent indent. Or the permanent indent, we note it with the superscript minus. And then, so you perform the annealing. So then you subject the surface to the thermal annealing at around 0.9 times the glass transition temperature. And again, you measure the volume of the pileups, which will have changed because you have some permanent densification that will have been released. And again, you measure the volume of the indent, which are in this case called VI minus and VA minus and VA plus, being the volume of the pileups. And by looking at this volume of the pileups and of the indent before and after annealing, and by looking at the difference of those, you can determine what was the fraction, what was the volume of the glass that was permanently densified, that is recovered upon annealing, and what is the volume of the glass that has been displaced by shear flow upon the indentation. So we are going to see what are the equation to get those two information. So the first thing is, what is the volume that is recovered? The recovered volume after annealing. So this recovered volume after annealing is the volume that was permanently densified. This is the volume that was permanently densified during the indentation, and that is going to be released when you anneal the glass, when the internal stress caused by the densified volume is released. So how can we get this recovered volume, this densified volume? So one way to do that is to express the volume of the glass before and after annealing. So before any indentation, so this is what the glass would look like. So this we can call it V0, V0. This is the volume of the glass before any indentation. So if we look at the volume of the glass after the indentation, but before the annealing, this volume of the glass is given by first the initial volume of the glass V0 before any indentation, plus the volume of the pileup. So this one is a creation of volume. So we can add now the volume of the pileup, which is Vi plus, but some volume has been lost. This is the volume of the indent. This volume has been lost, so we need to remove it. So the volume of the glass after the indentation is equal to the initial volume plus the volume of the pileup minus the volume that has been lost due to the permanent indent. And now if you look at the volume of the glass this time after the annealing, then again this is the same expression. So it's again the initial volume plus again the volume of the pileup, which is now potentially has changed due to the annealing, minus the volume that is lost here, the volume that is missing, which is Va minus. So now the question is, what is the volume that was densified? The volume that was densified is the volume that has been recovered during the annealing. So this volume is the difference of volume before and after annealing. The difference of volume before and after annealing is the volume that is recovered during the annealing, and this volume that is recovered during the annealing is the volume that was permanently densified. So the volume that was permanently densified can be used by just taking the volume of the glass after annealing minus the volume of the glass before annealing, and this gives you the volume that was permanently densified, which is equal to Va plus minus Vi plus. So this is the difference of the volume of the pileups before annealing and after annealing, and the difference of the volume of the indent, so Va minus minus Va minus. So this one is the difference of the volume of the pileups and the difference of the volume of the indent. The total difference of volume before and after annealing tells you the volume that has been densified. So this is the volume that was permanently densified during the indent. An expression that is usually very useful is to look at the fraction of recovered volume. The fraction of recovered volume is defined as usually we write it VR. This is the volume that was densified, so this is the volume that is recovered, divided by the volume of the indent, so the volume Vi minus. So this fraction, the fraction of the volume that was recovered during the annealing divided by the initial volume of the indent is the fraction of recovered volume, which is a quantity that is often looked to characterize what is the fraction of the volume that was due to the permanent densification as opposed to the shear flow. So this one gives you the fraction of the volume that was permanently densified with respect to the total change in volume that was either due to the shear flow or to the permanent densification. So this one is a quantity that goes between 0 to 100%. 0 would be a case where you have no densification at all. The indentation only induces some shear flow, but the volume, there is no permanent densification. 100% means that there is no shear flow at all. All the effect of the indentation was to create some permanent densification, and there was no shear flow at all. So now the question is, how do you get now the volume that was displaced due to shear flow? So volume displaced due to shear flow. One way to get this quantity, Vs, the volume that was displaced through the shear flow deformation, is to look at what was the volume of the indent, the volume of the initial indent. So this is the volume before annealing. This volume here that was creating during the indentation. This is the volume that is missing in the glass. So the question is, if this volume has been missing, it means that this volume either has been displaced or this volume has been permanently densified. So if we want to have only the part of this volume that has been displaced, we need to take this volume of the indent, Vi minus, and remove the fraction of the volume that was permanently densified, VD, which we just calculated. So if we take the difference, volume of the indent, initial indent, minus the volume that was permanently densified upon annealing, this one tells you the contribution of the shear flow. So this one is the volume that was displaced due to shear flow deformation. So by looking at the volume of the indent and the volume of the pileups before and after annealing, we can get those two quantities. We can get the volume that was permanently densified and the volume that was permanently displaced by shear flow. And those two volumes contribute to determining the hardness of the glass. So now let's see how the glass composition and the glass structure is controlling the hardness of glasses. So for this, it's always useful to start with chalcogenide glasses and especially germanium selenium. So for example, as we saw several times, if you have a fraction x of germanium and the rest a fraction of 1 minus x of selenium, this provides a simple system. You start with a pure selenium which has a coordination number of 2, so you just have some chains like this, and then you add more and more germanium that have a coordination number of 4 that has a tetrahedral environment. And that way, by changing the fraction of germanium, you can look at what is the effect of the connectivity of the glass on its properties. So we are going to do that here to see how the hardness of germanium selenium is changing with its connectivity. So this plot and table shows you the hardness of germanium selenium as a function of the average coordination number, that is to say, starting at 2, which is for pure selenium, up to 4, which is the case, the average coordination number for pure germanium. So as you can see here, if you look at the hardness, it's increasing pretty linearly with the average coordination number, which means that the more connected the glass is, the higher its hardness will be. So you can see here several properties of germanium selenium as a function of the average coordination number and as a function of composition. So as you can see here is that the hardness here, so you have two types of hardness, but the values are fairly similar to each other. Those are the second one is the Vickers hardness, that is measured by a Vickers indenter. The first one is a different type of hardness. What you can see here with those two types of hardness, the higher is the connectivity, the more germanium you put, the higher the hardness becomes. And in that sense, it's fairly similar to what we observed also for the Young's modulus. The Young's modulus also increases pretty much linearly with the fraction of germanium that you have in the glass. Which means that in this case, for those glasses, and it's something that is usually true for a lot of glasses as well, the hardness is fairly correlated to the Young's modulus and overall to the stiffness of the glass. Usually the stiffer the glass is, the higher its hardness will be. So in that case, both those properties will tend to increase with the connectivity of the glass. The more bonds you have, the higher will be the stiffness and the higher will be the hardness as well. So the second example we can look at is a sodium aluminosilicate glasses. So in this case, you have some sodium, a fraction x of sodium, you have a fraction y of alumina, and the rest is silica. And in this case, what you can look at is what is the non-bridging oxygen in this class? What is the fraction of non-bridging oxygen? So here, what you know is that whenever X is lower than Y, when there is more aluminum than sodium, then the sodium in this case are used to compensate the charge of the aluminum. The aluminum is wants to be fourfold coordinated, but aluminum has a charge of only 4 plus, so there is a deficit of plus charge. In that case, the aluminum need a sodium cation to compensate their charge. So as long as X is lower than Y, there is more aluminum. In that case, all the sodium are used to as charge compensator. They are compensating the charge of the aluminum. In that case, they are not creating any non-bridging oxygen. But as if there is more sodium than aluminum, then A part of the sodium will be used to compensate the charge of the aluminum, and the remaining sodium will be used to create some non-bridging oxygen. So what matters here is what is the excess sodium? What is the fraction of sodium that is used to create some non-bridging oxygen? So what you know is that as long as you have one aluminum, you will need one sodium to compensate its charge. So if you want to know what is the remaining fraction of sodium that will be used to create some non-bridging oxygen, you have to start by first the total fraction of sodium. You remove the fraction of Al2O3. Why? Because every time you have one aluminum, you will use one of this sodium to compensate the charge of the aluminum. So if you take the difference between those two, you take the total sodium minus the aluminum. The difference between those two will give you the concentration of excess sodium. This is the sodium that is not used to compensate the charge of the aluminum. So this is the sodium that is used to creating some non-bridging oxygen. And if you look at the hardness, the Vickers hardness in this case, as a function of this excess concentration of sodium, you see that the hardness is decreasing pretty much linearly with the average excess concentration of sodium. What does it mean? It means that the higher excess sodium you have, the more NBO you have, the more non-bridging oxygen you have. Each sodium creates one NBO, so the fraction of Na2O will give you the fraction of NBO. And the more NBO you have, the lower the hardness becomes. So again, it tells you that the more connected the glass is, the higher the hardness. If the connection is very high, if there are very few non-bridging oxygen, if the glass is very polymerized, you have a high hardness. And as you depolymerize the glass, as you add more and more non-bridging oxygen, the depolymerization is decreasing. There are fewer and fewer bonds, larger number of non-bridging oxygen, and in that case, the hardness is decreasing. So again, the higher the connectivity of the glass, typically the higher the hardness will be. The lower the connectivity, the lower the hardness. So let's take another example with sodium borate. If you look at sodium borate, again, you will see the same usual boron anomaly, which will lead to a maximum in hardness. So what is the explanation for this? The explanation is the same as the one we saw for the fictive temperature, the glass transition temperature of the glass, and for the thermal expansion. First, you start from pure B2O3 when there is no sodium. The question is, as you start to add some sodium, then what happens? The first thing that happens at the beginning is that all the sodium are used to create some fourfold coordinated boron. So the sodium in this case are used to increase the connectivity. They increase the connectivity of the network. They transform threefold coordinated boron into fourfold coordinated boron. In that case, since the connectivity is increasing, the hardness is increasing. But at some point, as you continue to add some sodium, then you will start to create some non-bridging oxygen. At some point, the sodium are used to depolymerize the glasses and not to create some fourfold coordinated boron anymore. At this point, when you create some non-bridging oxygen, you tend to now decrease the connectivity of the glass, and at this point, the hardness starts to decrease. So same as explanation as for the previous thing that we saw for sodium borate. First, you increase the connectivity when you create some fourfold boron. In that case, hardness is increasing quite significantly from 7 gigapascal up to almost 11 gigapascal. But at some point, when you switch to mechanism number 2, when you create some non-bridging oxygen, then you decrease the connectivity of the glass. And if you decrease the connectivity of the glass, the hardness is decreasing again. The next question is, how does the structure and the composition of glasses is controlling the propensity of the glass to deform using permanent densification or shear flow when the glass is indented? So here, this plot shows you the recovered volume fraction. So this is the fraction of the volume that is recovered upon annealing. So this is the fraction of the volume that was densified, the volume that is recovered upon the annealing minus divided by the volume that is created during the indent. So this is the quantity that we saw earlier. So this gives you the fraction of the volume that, with respect to the volume that is created during the indent, that is recovered during the annealing. So this tells you the fraction of the volume that is densified as opposed to displaced during shear flow. So what you can see here is that if you take silica, this fraction is very high, pretty close to 100%. What does it mean in that case? It means that during the indentation, most of the volume is densified and very little volume is displaced through shear flow. On the other hand, if you take, for example, a bulk metallic glasses, then this fraction is very, very high, very low, or close to 0%. It means that in this case, when you indent a bulk metallic glasses, there is very little permanent densification and most of the glass is actually displaced through shear flow, which means that the volume of the glass is not changing, it is just displaced due to the shear flow, so that when you anneal the glass, not much volume is recovered. The volume didn't change to begin with upon the indentation, so there is no densified volume. So the volume doesn't change before and after annealing. And in between, what we see is that in general, the fraction of recovered volume, so the fraction of volume that is permanently densified, has a very strong correlation with the Poisson's ratio. So what does it mean? It means that when you have a glass like silica, a glass that has a very high internal porosity, silica has a high internal porosity. Why? Because there is a lot of space left in between the tetrahedral silicon atoms. In that case, this glass, it's very easy for this glass to permanently densify because there is a lot of space left in between the atoms. In that case, since it's easy for the glass to permanently densify, the recovered fraction volume will be very high. It means that during the indentation, when you apply a load on the glass will primarily densified rather than showing some shear flow. And in that case, it also corresponds to a very low Poisson's ratio value. Why? Because when you apply the load, again, it's more favorable for the glass to densify itself rather than to expand laterally. So this corresponds to a very low Poisson's ratio. On the other hand, if you take a bulk metallic glasses are very compact glasses. There is very few space left in between the atoms. In that case, you end up with a very high Poisson's ratio, close to the maximum value, which is 0.5. Why? Because if you apply a longitudinal load on a bulk metallic glasses, since there is no space left in between the atoms, the glass has no choice when you apply a longitudinal load, but to expand laterally. So in this case, the Poisson's ratio will be very high, close to 0.4. And again, since the glass has a very low porosity, low internal porosity, very high packing, the bulk metallic glasses typically have a very high packing density. In that case, when you indent those glasses, you will have very little permanent densification and most of the glass will be displaced by shear flow. In that case, you will not have any recovered volume upon annealing. And in between, when you take some other glasses like sodium silicate, soda lime, etc., you will have a very good scaling between the Poisson's ratio and the volume that is recovered through annealing. Why? Because those two properties all depend on the underlying packing of the atomic ratio. So if you go from here, silica, high internal porosity or very low packing, and if you go up to the type of glasses that have a very low porosity and high packing, then the Poisson's ratio will be increasing and the recovered volume will be decreasing, which means that for silica, the primary mechanism upon the indentation will be permanent densification. This is what will be controlling the hardness. The hardness will be controlled by the permanent densification because there is very little shear flow. But when you go to a glass with a high packing, That is to say, when you add more and more network modifier, for example, since the network modifier tend to occupy the space left in between the silicate network, the more modifier you put, the higher the packing of the glass. When you increase the packing, the Poisson's ratio is increasing, and the recovered volume is decreasing, which means that in this case, the primary mechanism will be shear flow. You will have very little permanent densification. So what will be limiting the hardness, what will be controlling the hardness in this case will be the shear flow deformation. So typically the propensity of the glass to show permanent densification or shear flow is primarily controlled by the packing. So when the packing is increasing, you will go from permanent densification up to shear flow, which is the primary mechanism when you have a glass with a very high packing. So now the question is, how can we use this information to predict hardness? So what has been observed is that there is a direct relationship between the hardness of glasses and the number of constraints per atom that is given within the framework of topological constraint theory. So the idea is as follows. First, to make a material cohesive, you need some constraints between the atoms. Otherwise, if there is no connection, no constraints in between the atoms, then the material is not cohesive. It would have a zero hardness. You need a minimum number of bonds per atom to make it cohesive. So this number of bonds is a critical number of constraints per atom that is needed to make a material cohesive, that is to say, to have a hardness that is not zero. Then the idea is that starting from this initial number of constraints that is needed to make the material cohesive, to make the glass cohesive. Cohesive means that it wants to stay together. It is rigid. It doesn't want to, the atoms are not just free to be separated from each other. Started from this initial number of constraints, that is the critical number of constraints that you need to make the glass cohesive. Then each additional number of constraints, so this is the number of constraints per atom. Each additional number of constraints added in addition to the critical number of constraints will contribute to increase the hardness. So you have a linear relationship between the hardness of the glass and the difference between the number of constraints minus the critical number of constraints. Any additional constraints in addition to the number of constraints will contribute to increase the hardness of the glass, and the proportionality constant is just a given constant that depends on the type of bonds that is added. If the bonds are very strong, then the constraints will increase hardness a lot. If the bonds are less strong, then the constraints will tend to increase hardness in a lower fashion. So in any case, you have a linear relationship between the difference between the number of constraints per atom minus the critical number of constraints needed to make the material cohesive, and the hardness that can be measured by nano-indentation. Indeed, for example, if you plot the hardness as a function of the number of constraints for germanium-selenium, with a fraction x of germanium and the rest being selenium, then you find that you have a fairly linear relationship between hardness and the number of constraints, which is that the more number of constraints that you have, the higher will be the hardness. Each additional constraint contributes to increasing the hardness of the glass. So this relationship between hardness and number of constraints per atom has been verified for many types of glasses, and especially for oxide glasses. So here, this is an example for a sodium-calcium borate glasses, where you have a given fraction x of sodium oxide, a given fraction y of calcium oxide, and the rest being B2O3. And what you can do is to calculate the number of constraints as a function of x and y. And here, if you measure the hardness of those glasses, you see that indeed, again, so you have here two different hardness measured with two different fashion and two different load, two different techniques. But in both cases, you observe that the hardness is increasing linearly with the number of constraints. You have a direct relationship. You have a proportionality constant between the hardness and the number of constraints minus the critical number of constraints that is needed to make the material cohesive. And in the case of oxide glasses, very often what is observed is that the critical number of constraints that is needed to make the material cohesive is 2.5. Why? So if you have three number of constraints, this is the number of constraints per atom that is needed to make a material completely rigid in 3 dimension. On the other hand, if you have a number of constraints of 2, number of constraints of 2 per atom, this is the minimum number of constraints that is needed to make a material rigid in 1 dimension. Why? For example, if you take the pure selenium, if you just have some chains of selenium atoms, then this is the number of constraints that you would have. You would have 2 constraints per atom. You would have for each selenium 1 bond bending constraints and 2 bond stretching constraints that are always shared by 2 atoms. So altogether for selenium, which is a type of glass that is only rigid in 1 dimension, that is to say you just have some chains, some infinite change of selenium, then in that case you have a number of constraints of 2. So the number of constraints per atom being 2 is what is needed to make a glass rigid in 1 dimension. And for oxide glasses, what is observed is that to have a hardness that is higher than 0, you need a number of constraints per atom of 2.5, which is the number of constraints that is needed to make a material rigid in 2 dimensions. And this corresponds to the point at which you start to have a hardness that is initially 0, and as soon as you exceed this threshold of 2.5, then the material starts to be rigid in 2 dimensions and the hardness starts to increase. Hardness now becomes larger than 0. So what is observed for many oxide glasses, so borate glasses, phosphate glasses, and silicate glasses, is that altogether hardness is equal to a given proportionality constant times the number of constraints per atom minus 2.5, 2.5 being the critical number of constraints that you need for the hardness to be non-zero. So this is typically what is observed for oxide glasses. So based on that, what you can typically do is to, for a given glass, measure hardness for a few composition. Based on that, if you know the number of constraints per atom, you can determine what is this proportionality constant dH divided by dN. This is the how much each additional constraints contribute to increase the hardness. And once you know this proportionality constant, once you have measured hardness for a few composition, then you can analytically calculate the number of constraints per atom for every composition. And at this point, you are able to predict what would be the hardness for any composition. So for example, this other plot at the bottom here shows you the hardness that is predicted. So here this blue line is the hardness that is predicted by this model. How do you predict this hardness? First, you calculate the number of constraints in glasses, number of constraints per atom as a function of composition, just like we calculated the number of constraints per atom, for example, in sodium silicate. Then you you remove 2.5 from this value, you multiply by this constant dH over dN that you have measured experimentally, and based on that you can predict what would be the hardness for every composition by first calculating the number of constraints per atom, and based on that calculating a predicted hardness. So this blue line is the predicted hardness value, which later on you can compare with experimental value, which, as you can see here, there is a pretty good agreement between the model, the predicted hardness value, and the experimental measurements, which shows that there is a very good accuracy in this model to predict hardness of borate glasses. So this is a very interesting theory because it means that now if you take, as soon as you have determined this constant dH over dN, it means that as soon as you are able to calculate the number of constraints per atom as a function of composition. And if you know that this is equal to 2.5, then based on this information, you are able to predict the hardness for any composition. So it tells you that if you plot the hardness as a function of composition, you can now identify the region where hardness is maximum and try to synthesize those glasses. So it means that by using this model, you can theoretically predict which composition will give you the highest number of constraints per atom and consequently the highest hardness. And if what you want is to design a new glass with an increased hardness value, then you can predict which composition X and Y, which fraction of sodium and calcium will give you the highest hardness value. And based on that, you can pinpoint what will be the promising composition that will maximize the hardness of the glass. So the advantage of this theory is that you can predict directly the relationship between composition and hardness. And as a consequently, you can, if you want to design a glass with a very high hardness, you can directly predict which composition are the most promising, rather than just making a lot of glasses and randomly check the hardness of those glasses until you find a glass that meets the hardness requirement that you want for your glass. This is another example for a sodium aluminoborosilicate, so a more complex glasses. Again, the approach is as follows. First, you calculate the number of constraints per atom as a function of composition. Here, composition mostly depend on the X, the fraction of aluminum, but the composition, the number of constraints also depend on the fraction of silicon, fraction of oxygen, fraction of threefold and fourfold boron, etc. Based on that, you can calculate the number of constraints, and if you know the number of constraints per atom, you know that the critical number of constraints to make the glass rigid is 2.5. Based on that, if you can determine this constant, which here has been determined to be 7.2 gigapascal based on experiments, based on that, you can predict the hardness for any composition. And based on that, you can see here, so the solid square are the hardness value that are measured, and the empty square are the one that are predicted. And you see you have a pretty good agreement between the predicted and measured value. So based on that, you can say that if what you want is a maximum hardness, then you can say that this is the composition that will give you maximum hardness. And this can accelerate the design of glasses by directly looking at the promising composition rather than synthesizing all those glasses one by one. So in conclusion, what we have seen is that hardness is not a material property. The value of the hardness for given materials depend on the techniques that is used to measure the hardness. So different techniques will give you different hardness value, but it's a property that typically depends on two things. First, when you apply a load on a glass, how much does the glass shows any permanent densification, and how much does it deform through shear flow? Those two phenomena that either change the volume of the glass or doesn't change the volume of the glass but just displace some of the region of the glass are the two things that can determine the hardness of glasses. And typically what is observed is that the connectivity of the glass and also the bond energy of the atoms within the glass are the two things that tends to make the hardness higher. The more connected the glass is, or the higher the bond energy, the higher will be the hardness. And in that sense, hardness is typically pretty well correlated to the stiffness of the glass, or the Young's modulus, which also increase with the connectivity and the bond energy of the atoms within the glass. And the last thing is that, as we saw, by using this relationship that tells you that the hardness is proportional to the number of constraints minus the critical number of constraints that is needed to make the material cohesive, it means that if you know the number of constraints within the glass, and if you know how much each constraint contributes to increasing the hardness of a glasses, you will be able to predict what will be the hardness as a function of composition. So in this formula, we see the two things that we just discussed. The more connected the glass is, so the higher the number of constraints, the higher will be the hardness. And also, this term here corresponds to the strength of the atoms, the energy of each heteratomic bond. So here, if the bonds have a very high energy, this term delta H dH over dN will be very high. So this term is linked to the bond energy. So it captures how much, as you increase the number of constraints, how much does it increase the hardness. So this term captures this, the NC terms captures the connectivity of the glass. The higher the connectivity, the higher the hardness. And this term, dH over dN, captures the bond energy. And those two things can be used to increase the hardness of glasses. Thank you for watching this video. So we've saw the stiffness. Now we talked about the hardness. The last thing that we will see in the next chapter is about the toughness of glasses and how the toughness, the resistance to fracture, depends on the glass composition.